Good evening, good morning, good afternoon, depending on where you're watching. So this is the video demonstration of the Stereo Vision project. So to start with, I'm going to click on calibration to capture like around 11 to 15 pictures of the chessboard. So in order not to take much of our time, I'm going to capture the 15. I'm going to capture 13 in this case, but I'm going to pause it. So I'm going to play it back after I must have captured and then done some things. So I have captured the 13 pictures. So right now I click on calibrate. Then after that, so that's the calibration saved, RMS, that's root mean square. So now I'm going to click on back, then click on capture. So at this point, I will now click on, so I'm going to click on capture left. So in this case, my baseline is going to be around, let me say 10 centimeter, that is 0.1 meter. So this is the image I'm considering. So when I capture left, so it has saved left. So the distance between this object and the phone is also 10 centimeter, which is like 0.1 meter. I captured that too. So right now I click on back again to go to the processing. So in this case, the run pipeline is going to show me the 3D image. The way so it's going to show me the ORB matches. That is the 3D appearance between the right what is it called, the left capture and the right capture, as you have seen in the previous menu. So after this, then I click on back to now take my depth result. So in this part, so as you can see in this part, I have 0.1 meters, which I have mentioned earlier. So that's my baseline. So from here, I now click on generate point cloud. So it's processing. So while it's processing, so I'm connecting my USB from my computer to the phone. So we have to wait for a while for it to, now it has generated the my cloud.ply file. So in this case, we now come to, I come back to my what is it called, Android Studio project. From there, I now export my cloud.ply file. How do I do? Okay, now I have to come to video to show how the process is like. Then this is my Android Studio project. From Android Studio, I come to so I come to view menu, then I come to tool windows. Then from tool window, then I click on device explorer. So from device explorer, a dialog box is going to show up. Then from there, I will now click on data. Let me bring it closer. Data. Then I come to example. I think it's way down, so I need to use this in order to make it faster. Okay, come example. So I need to trace my project. I have some projects here, so I have to be very careful. So this is my PCC module, this is my calibration project, and this is my vision project. Okay, now this is my stereo vision project. This is the one that is peculiar to this project. Then I look for that part that has, I look for file, yeah. File, then yeah, this is my cloud.ply file. Then I save it. I download it to any location I deem fit. So let me put it in my download folder. So then I save it. Let me overwrite the previous one I did. The next video I'm going to do is going to show how I'm going to process um, the cloud.ply file, so that it will be more detailed. So from there I will show how I was able to capture the image at the unprocessed, the filtered and the unfiltered image. The unfiltered image is the image I got where is the image that came up when I loaded my what is it called, my file. So the filtered one is the one that is the post filter stage of my particular image. I'll show the details. So I'm going to add the video to this one I made with my phone, so because the next one will be made with my computer. Well, hello everyone. For my StereoVision project, I will start with processing a high density point cloud. I quickly discovered that manually cleaning outlier noise in standard software was not only tedious but extremely inefficient. Today, I will demonstrate how I moved from uh, a manual labor-intensive workflow to an automated script solution using Python and Open3D. So now let's get started. So now for processing this kind of projects, was particularly on StereoVision, there are two most common software that can be used, which is MeshLab and Cloud Compare. But I think it's for me. I think MeshLab is a little bit more ideal for me. So that's why I chose to use MeshLab. So now I am now going to import the um, cloud.pl Wi-Fi that I mentioned earlier. So for us to be able to see the process. So this is it, and this is how it looks like. So for more clarity, I would like to make some adjustments so that we'll be able to see how those points are like. So all these points are our image that we are trying to process. So now I'm going to talk about the problems associated with this particular project. When you look at most of all these points, or let me say some of these points are noises, or sometimes I can also call them outliers. So, but it is almost impossible for human eyes to project or to be able to detect which of these points are the image and which of them are the noises. So in this case now we've been able to generate like 5,376 vertices from the raw data. So we'd like to show the difference between these vertices, or let me say between this particular image from the raw data and the cleaned one. So I would like to also say that getting the, or let me say eliminating the outliers or the noises in this kind of image using the mesh lab software will be somehow cumbersome and time consuming, as I have said from the beginning of this particular section of the video. So part of the problem is that initially I attempted to clean the data using mesh lab. While mesh lab is a powerful tool, it requires manual selection of noise with a point cloud of this density. Selecting outliers manually is prone to human error and consumes a massive amount of time. I realized that if I wanted an accurate, reproducible result, I needed a programmable approach. Now, this is the solution I prepared. To solve this, I developed a Python script. As you can see here, I developed a Python script utilizing the Open3D library. Instead of manual selection, the script applies a statistical outlier removal algorithm. It analyzes the neighborhood of every point and automatically removes those that deviate from the average distance. This ensures that cleaning process is objective and identical every time it runs. So this is from the execution. Here is the execution script that I've shown, and I am running it with a clean virtual environment to ensure all dependencies are managed correctly. So I executed this particular clean.point script, and the script is after processing, that's when it now generated this particular one, as I was going to load it into MeshLab. So this is the one from the raw data. Let me close this, and this particular one is the cleaned one. We will see clearly right now from this particular image that this one is clearer. I mean, yeah, it has low points in comparison with the first one because the noises have been removed. Let me make some selections, make some adjustments for more clarity. You can see that most of the noises, or let me say the outliers that are around these places, around these locations, have been removed, leaving us with these remaining points. So all these points are the real image from our particular projects. Yeah, so as you can see here, the current vertices is 4,900 and something, which means around 500 points have been removed. So that's about the results. What else do I have to say in this particular video? Yeah. So and there we have it. The terminal confirms the filtering is complete and the file has been saved. This workflow is significantly faster, more accurate, and much more scalable than manual cleaning. This output is now ready for the next stage of my StereoVision pipeline. So automating this cleaning process allowed me to maintain the integrity of my data set while reclaiming hours